This talk is inspired by lots of questions I got the last half year or so. People telling me, oh, we want to use your quick check tool for load testing. And you think, okay. And then other people saying, I'm doing load testing with quick check and I get really weird shrinking behavior. Other people saying, how do you do this load testing with quick check? And, okay, what's load testing? So, load testing I found, because I started thinking about this and read a little bit of papers and things like that about load testing. And it turns out that you use load testing normally to determine the maximum sustainable load that your system can handle. That's kind of the general way of doing it. And there's stress testing, there's lots of load testing. But if you say I'm going to do load testing, the thing you want to find out is how much load can this system handle. In fact, beer before it collapses, before it starts doing very strange things. So that's what you want to find out with load testing. And then there's a secondary objective, and that's to reveal program errors that typically only appear on the system with a high load. In other words, those people, they don't have good testing technology, and they try to do that as late as possible when the system is built and puts a lot of load on it, and then they say, oh look, there's an error in the code because of concurrency, because they couldn't possibly find that much earlier in the chain. Or they probably find out, oh, this is memory leaking, because they couldn't possibly run a tool that checks for memory leaks just before, right? So they find that out at the latest possible moment when they build the whole system and it puts load on it. So there's two things that people use load testing for. And there's also some timing sensitive parts. And you can imagine actually that certain bugs really are only seen when you put a lot of load on the system, even if you have good testing technology. But the real thing you want to do is to find the sustainable load. Okay. And then the thing is that if you do load testing, at least the literature tells you, that you validate your system under a given realistic load, under a given load. And this is typically defined in events coming from the outside. So you can have user events or transactions, and that's how you measure load. And in the keynote for this morning, we heard Kevin talking about, oh look, we have 311 million threads, and we generate them in 4.5 minutes. That is 20,000 threads per second. That's a measure on measuring load. How much things can you do per second? That's what you do there. Now, quick check only verifies functional behavior. It has nothing to do with load testing. Quick check creates unrealistic examples and not realistic examples. That's exactly what quick check is very good at. And quick check does not test for a longer period. The shorter the better. That's what the quick is in quick check. Right? So, why would you use quick check for load testing? You could wonder. And I didn't get any satisfactory answer from the community. So I started thinking a little bit myself. What could people want to achieve by doing this load testing? Probably the secondary objective is actually their main objective. Probably they want to find errors in their code by using load testing. And quick check is pretty good in finding errors, so that's probably why this came into their mind. Or they feel that they have only a few events in their normal load test. They would like to vary a little bit more the events they put in the load test. So still realistic, but more variation. And QuickCheck has this fantastic random generation tool, so you could probably use QuickCheck to make more randomly varied kind of things. Because if you only load test with 2 users, a heavy user and a light user, and that's your profile, then you probably don't hit those errors which you need for the secondary objective. It's probably very realistic, but you won't hit the secondary objective. And that's probably what you really want to do by varying profiles. The other thing which might be the case, because this is just me making it up, QuickCheck can generate large tests. And QuickCheck runs extremely many tests very fast. People that use QuickCheck in the beginning, novel users, often get the expression, the feeling that, oh, this is hammering my system. Right? And hammering my system, load, right? That feeling is then staying alive. And they think, oh, this is actually a tool that hammers my system a lot. And therefore it might be loading the system a lot, and therefore it might find just load testing bugs. So there might be reasons that people think, oh, quick check and load testing fit well together. So I then started to think a little bit more about load testing, and it's kind of intriguing, so did it. How do we get realistic load? That's then the big question that we do. If we want to use load testing, how do we get our realistic load? And there's two different ways of doing that. You can either say, okay, I have kind of user scenarios that are, you have a number of things that can happen. That's called the user scenario. And this user is, for example, watching videos on my server, and this user is listening to MP3 files on my system. And the watching video guy or girl is much more heavy on the system than listening to the MP3 file. So there's two different kind of users. And you say, what does the user do? Starts a movie, sits there for 1.5 hours, stops the movie, pauses a few times in the middle, probably, whatever. The music is only 1.5 hours and comes much more frequently. So you have user scenarios. That's one way of doing that. And for example, the Megacode tool, the Megaload tool from Erlang Solutions is typically such a tool that exploits that way of putting user scenarios in place and then running it. The other way of measuring it is in events per second. So how many transactions can we do per second? How many billing transactions can we do? How many users can click on a certain button per second without the system falling down? And I think the Klarna system, Kronos, is a typical example of such a load testing tool, where you just say, run those number of things per second, and then look what the event is. Both are load testing tools. They have a slightly different angle, but you could both use them for real load testing instead of. The top one is probably more realistic when you have stateful systems. When you have a stateful system, you can't really say so much about events per second in the same way as you do when you have user scenarios. That's my thing. So here you would express the load in number of users per scenario. So you have 200 heavy users and 500 MP3 file users at the same time. Whereas here you would say, I have this number of events per second. So 10,000 starting a movie event per second, or 20,000 stopping a movie event per second, or whatever we want to do. Let's make this a bit more concrete and look at a concrete example. Let's look at a very simple resource management. There's only two operations. You can use the resource and you can free the resource. In a user scenario-like thing, you could have a use event, you keep your resource for a while, and then you have a free event. That's the kind of heavy user. And you can have another user which uses the resource, keeps it for a while, short while, and then frees the resource. Now, if you do load testing, you're interested in how many of those two users can you have in the system at the same time. And as you can imagine, this gives you some local minima and maxima. Right? It can be that you can have a lot of 500 of those, but then only 2 of those, or you can have 200 of those and then 300 of those, etc. So you balance it a little bit. And you're probably interested in both answers. How many of this, how many of that, how many of the combined time makes good sense here. Events don't make sense. In this setting, you would do that differently, I'm sure. But you can't say, well, what happens if we have 100 users used per second and only 23 per second? And your system goes further, but it's not such a realistic thing to start with measuring that kind of events. So let's concentrate more on the top level, where your primary objective is how many users can we find. I make a resource manager. Tom.
Back. I think one of the things here, when we talk about load testing here, the SLA is key here. It's not only that how many users can we handle, but what is actually the experience from each type of user.
Ah, right. Yeah.
So there's something here in for instance, user 2. It's good to have in the system because they use the resource very short. But if you have the number 1 users, the expected user latency time will grow because they're sitting there waiting. So there's some other measurements that we need around this.
A real load testing tool takes care of that kind of thing. So this dimension I completely ignored in my presentation and in the paper. There are many other aspects of load. So absolutely right. Load testing is more than finding errors. Load testing is about non-functional requirements. What is the expectation of the user?
Which would be nice to have a quick check, by the way.
There are people that ask, why don't you use quick check for load testing? My point is, okay, this simple resource manager has it's just an Erlang function. It has two arguments in the loop, the number of users that it has and the number of recently new users that dropped in, just to make it non-determinate, more or less. So we have a receive, which says a use, and it will just say yes. And we have a free, and it will just increase the loop value with putting a 0 in the second one. So you free the user, but you also have a 0 for the new user. So if you do a lot of users after each other, the idea is the load on your system is more heavy than when you have a number of users and then a free and then another number of users and a free. So I wanted to mimic that a little bit to get non-determinism, because if the number of users together with the new users is less than 1,000, everything works perfectly well, but otherwise it crashes. So I could crash when I have 500 users doing the use, right? Without any free in between. So 500 would crash the server if I don't get any free in between. But I could also have 600 users and had a free after the 100th user or whatever. So there are a number of ways where I can crash this system. So this landscape is going on. Right, we are going to test this. We are going to do naive quick check testing, because some people think you can use that. So we make a user. It gets the process identifier of the resource manager as input and the time that it should keep the resource. We use the resource, we sleep for a while, and then we free the resource. If I want to spawn off a number of those users, I use the users function, which gets the process identifier of the resource manager, and n, which is the number of users I want to spawn, and the time. I call this user function and I recurse. In the end, I return true because quick check lies true. I have a load property. I say for all n natural numbers, start a resource manager and run n users, all taking 100. Yeah? Super naive, this is not going to work. But this might be a way to do it. You run that, you get 100 tests, you look at the statistics that come out of that, and you see, oh, there's only 1% of the cases, or one test case, where I got actually 27 users, the rest is less. This is not really load testing, right? 27 users is even this system. So this is not the way to do it. And anyone doing some quick checking knows that. The question then is, of course, we know that NAT is not going up to numbers bigger than, say, 27 or even if it's 40, it's nothing. What to put there? That's the question. What do we put there?
Your own generator?
Yeah, of course your own generator, but what would that generator be?
Something you expect to be your maximum and generate the value somewhere around there.
Oh, I like that, yeah.
Maybe the amount of concurrency you want in the system at one time?
Hmm? Not a fixed number. So you would like to have a generator. And the one you proposed is something around the number you expect to fail. How do you know that? You haven't seen the source code. Yeah, okay, showed you. How do you know that it crashes around 1,000, right? If you have a big system, you have no clue. So someone told you, hey, it crashes around 1,000, and you say, okay, then I try until 1,010, and I pick a number something in that range, and you would probably not start at 0, but probably start at 900. But why?
A logarithmic distribution
Would be much better, much better. So this is a uniform distribution. So that's one thing. The other thing people tend to do is to take a very big number there. Then it's absolutely sure, if I can handle this, I'm very happy, so I don't care. So let's take a very big number. And it's also a bit where do you start and where do you stop, right? But the logarithm would be even better, but it doesn't really work because in quick check, and I come to that in a second. The previous test doesn't know about the next test. So there's no growth. That's it. Anyway, if you do this, someone has told you around 2,000, then what you get, if you choose this generator, is you pick an arbitrary number in this range, and most of those numbers, 90% of the case, you pick before the 1,000. And that's okay, but most of those tests, as you will notice then, when you run, they will pass. So you run, say, 100 tests, and one of them can fail. So the average failing time takes about 90 tests. I tried it a few times, it's about 90 tests. And then you fail. If every test takes an hour, you're not happy. In load testing, because it has to do with time, it might equally take a long time. That's not very nice. If you do this, you can say, oh, we always fail at the first test. I only had once that I actually run a successful test. Because you will normally pick a number over 1,000 here. Say 90% of the time, you pick a big number. So you will almost always overload your system dramatically. And that's not really load testing, that's stress testing. You put lots of stress on it, and you find the number and it crashes, but it doesn't really tell you where it is. So you try to start shrinking, and then shrinking takes ages, because you start from 0 and you have to climb up slowly. Right? That's the problem. So this kind of test takes, the test itself takes time, you have to imagine that. If you have a small number of users, then you can argue that you have small numbers of users, that the testing time is probably also smaller, because probably if you run a lot of users, your testing time increases by that. If you fail, you want to have a sustainable load. So the failing is not giving you the sustainable load. The thing just before failing gives you the sustainable load. That's what you really want to find out. So you start shrinking, and you look at your shrinking alternative. So the first alternative thing, where I go close to the limit that I have heard people say that 1,000 might be risky, it takes me 80 tests, probably, to get there. One test that is actually failing then, that's 996. And then I get this fantastic shrinking tree. And it stops at 989. That's my sustainable load, in this case. It fails at 999. No, sorry, the sustainable load is 988. Well, that's very precise, isn't it? The other one, you run one test to fail, because it will pick 9,105, and that fails. Right? And then you have your shrinking tree, and in this case, the shrinking tree is actually not even so much longer than that one. In many cases, this one is much longer than that one, but not much, in the sense that it's binary search, would have fun. This also ends up with, say, 989 is a problem case, 988 we can handle. So we are. But if you look at the shrinking, and if you think of each test taking time, you're not happy. Why, Thomas, are you trying 0 once more? Right? Is that really a good test? And then 2, and 6, yeah, okay, it still works for 6, and 40, yeah, it works for 14. Right? You don't feel like this is how I would have done it when I would do this manually. I would probably, if I find this failing, I would probably jump to 500 instead. Right? That's how you like to do it. So, first problem, you run 80 tests, jumping up and down in the search space to find a number that fails. So you don't learn anything from earlier tests. And even in the shrinking, you don't consider any earlier tests, which you might have seen already. That's problem number 1. Problem number 2 is that if you would have done a manual binary search, it would have taken less tests to get to the optimal shrinking value. You would just start from the top, take half the number, go up, go down a little bit in that space, and you would end up with the same kind of value, but much quicker. And then the other observation that is very important as well, the exact bound is not that important. It doesn't matter that it is 988, right? If you see that you go up to 958 here, and it still works, and 990 fails, then you would probably say, it's somewhere around 950. You wouldn't care to do all those tests after that to find a precise number. Okay? So that's what's missing in this naive approach. Time to get slightly less naive. So, but no, more naive, right? So what we do now is we say, well, this was just a case where you have 2 users. One user which had 100 milliseconds, and now you want to have 2 or 3 user profiles. So we make user profiles where one listens 100 milliseconds to the resource, the other one 200 milliseconds, and we have one that listens 400 milliseconds to the resource. You have 3 user profiles. You make those users by taking a vector of the arbitrary number here that you pick. So you make a vector of 9,000 elements, right? is naive, John, I know. But this is how people might do this. Actually, I've seen it. So what happens now is that you find your failing case immediately, but you would like to be reported in the sense of, okay, if I run 500 users of this kind and 200 of that, and then things are going wrong. You get some kind of report in the end, but it takes ages to shrink this. It takes more than 8,000 shrinking steps to actually get there. And if each shrinking step only takes a second, I get annoyed. If it takes a minute, everyone gets annoyed. If it takes an hour, even the system collapses, right? So this is not the way to go, and this is not even so much more sophisticated. You would probably have user profiles with far more variation in the shrinking. So if people say, I tried load testing with quick check, and the switch stops shrinking because shrinking doesn't work, we now know why, right? Because it's not made for that. And also then you shouldn't use quick check, because if shrinking doesn't work, you won't find your kind of thing. Then you just use a random generator. Why should you random generators? Okay, thousands of shrinking steps, naive. Let's do it better. What is a load test? A load test is one test actually where the load is constantly increasing. The load is increasing according to strategy, logarithmic, exponential, linear, whatever you decide. But you increase the load. And quick check should then be used to increase the values for consecutive tests. That's not what quick check is doing. Quick check takes a value and then the next time it takes a completely arbitrary value, not knowing about the history. So I wrote a little thing on top of quick check. I could, of course, I have the possibility to go into quick check and to make that into quick check, but I didn't do that. On top of quick check, I built something which is called load check. So anyone can do that, even with any quick check implementation. You can build on top of that. Quick check is a framework where you can add things. So quickly, because I'm running out of time, what you do, there's this parameter thing in there. You give it a test number. Test number is now some parameter of quick check, which you instantiate to 0 normally. I take the power, and for exponential growth, I write my property then as full and exponential 10, run this, and my load check will then take 0, 1, 10, 100, 1,000, and then will fail. You only need 4 tests. So this is nice because it looks almost the same as we had at the beginning. I will provide this one so you don't have to care about it. You just use a load test generator, that's fine. Your property looks exactly the same, but you need load check instead of normal check. Load check is written as follows. No, sorry, this is the shrinking. You have to shrink down according to binary search. So you have to implement shrinking for that load testing. You can easily in quick check add your own shrinking alternatives. This shrinking alternative is basically doing binary search in the shrinking. Okay, but that's provided, so you don't have to do that. If you figure that, and this is what you get. You start at 1,000 and you shrink to 550, not to 500, because 100 was already tested. Okay, so in the middle is 550, and then you go down and you fail the in this case, not the actual 9, 8, 9 that we had before. This is different, and that's because the system is slightly optimistic. Then you of course realize that you should actually stop here, because if you have an accuracy of about 100, if that's what you want to stop here, so you put your accuracy into the generator and you stop at, you fail when you are close enough to that margin. So your expected maximum sustainable load is the failing test case X minus the margin. That's what still would work. So you put this margin in there. In the paper you can read how you do this margin thing, but that's trivial, you can do that. You can still run that. This test case, the other one is now very much optimized. So the other one takes only this many tests, and you've got 5 tests plus 4, 9 tests. That is a big improvement. This one is also improved, the naive one, but far too less improved. This is not good, because you still have this enormous kind of stupid way of looking at all the different users. So what you have to do there is to be slightly smarter as well. You would like, it doesn't matter which position in the list those users have normally. You don't really care too much. So you would just pick 3 numbers with the triple generator that I also described in the paper. You have light, normal, and heavy users in this way, and you would run with them, and that would shrink much better. Actually, this is how you implement triple. You can read in the paper. What's interesting is the shrinking behavior that I implemented in triple. Is you start with a number, 1,400, 200. Something goes wrong. You decrease the first one first until things will start working, and then you start decreasing the second one, and then you start decreasing the third one, so that you get a kind of a nice way of explaining this is what you can have. Make bigger jumps in your shrinking. That is much better for load testing than independent shrinking, so they are depending on each other. And then you could shrink light, normal, heavy, or heavy, normal, light, depending on what you want to shrink first, what you would test. Okay, rounding up. You use load testing to find the maximum sustainable load, sometimes also for finding errors. Standard quick check generators are not very suitable for that, but with this improved generators, you could do much more, although you still need a load testing tool to actually do this timing thing and then do the other parts of the story. But at least those generators help you if you want to generate users for your system in making them shrink as well. That's my message.